I mean, if we went back to the mole method, if we moved this 3 over here and moved this 2 over here, it's not just similar, it's identical. Do you see that the math is identical? We're writing it out in a different, slightly different fashion, and that's because we're not using the balanced equation, we're using those charges. But if you think back to this balanced equation, these coefficients that we used in the calculation, these coefficients are what they are based on these subscripts, right? And these subscripts are what they are based on those charges. So why not just go ahead and calculate on charge? Does that make sense? It's a shortcut system to where you don't need a balanced equation. Go ahead.
Why did you do the 1-to-1 equivalence of sulfur aluminum?
Because in the two equivalent weight terms, we factor out the difference in charge between those two particles. They react in different proportions up here because they have differences in charge, right? Now, for example, if we had been reacting sulfur with magnesium, then it would just be a 1-to-1 ratio, correct? So what we're doing with equivalence is we're factoring, if they have a different charge, they react in a different ratio. But if we factor out that difference, then you put them all back on a 1-to-1. I don't know if that's any better or not. But what you're doing is you're factoring out the one thing that makes them go in different proportions. And by doing that, it will always set it as a 1-to-1 ratio. If you wrote this down in the notes, put a big star by that and write the word always. You don't have to think about what's the ratio going to be. It's absolutely and always 1-to-1.
So it's mainly really canceling units.
Yeah. Other question? Number 22. Zinc is reacted with lead-2 nitrate to produce solid lead. How many grams of lead can be produced from 4.50 grams of zinc? Now this is also one that you could do by the mole method if you wanted to, but that would require writing out the balanced equation. And if you made a mistake in putting together the formula of lead-2 nitrate, then you're doomed, right? Because your reactions messed up and your ratios are going to be messed up. Lots of things are going to be messed up. But approaching this one by equivalence isn't so bad, because really the nitrate has nothing to do with it. We're trying to relate lead-2 and zinc, right? The nitrate is really kind of irrelevant. We're trying to relate lead with zinc. So we have our 4.50 grams of zinc. And we want to convert that to equivalence. What does the periodic table tell you about zinc? 65.39 grams is 2 equivalents. Yes? One equivalent of zinc reacts with one equivalent of lead. Always. And then we need to go from equivalents of lead to grams of lead. What does the periodic table tell you about lead? Its mass is 207.2. Now, the periodic table doesn't help you in terms of charge on that one, because lead has multiple possibilities, but the problem itself says lead 2, correct? Zinc is one of those metals that you know it's charged, it never varies, and the compound it has to be 2. But lead does vary. If you were working that same problem by the mole method, it'd probably take you about 10 minutes. Because you'd have to write out your balanced equation and make sure you got all your products in there and everything balances out atomically, and then you could start into your math. But do you see how we've circumvented the need for a balanced equation? All right. Do number 23 on your own. First step is on the board. Isn't iron one of those metals with variable charge? How do you know it's a 3 then?
Because it says iron
Name
sulfate.
says so, right? Iron 3 sulfate. How do we go from iron to sulfuric acid? 1 to 1. And then we would need to go from equivalence of sulfuric acid to grams. This is 98.07. Let's go with 1 then. And how many equivalents is that? 2. Are you okay looking at H2SO4 and telling that the charge is 2? Question about that? If there's a question, please ask. Any question about that? 27. Take a couple minutes to work on 27. What is the charge of copper in this particular instance? +1, because we've got CuCl and chloride is a -1, right? So in this particular case, the copper is just a +1. 1 equivalent copper reacts with 1 equivalent calcium, or 1 equivalent of anything for that matter. And then we want to relate equivalence of calcium to grams. What's the charge of calcium? 2. And so this is what your setup would look like. Question about that? Question. Do you see how we're pulling most of the information from this problem from the periodic table, not from the problem itself? You know an awful lot about that periodic table by now. And so we're incorporating that information into our system. And now we're getting to ones that are more similar to that one that we had at the very beginning. The one that looked impossible, impossibly hard. In this case, we've got an unknown vanadium nitrate compound. How can it be unknown if we know it's vanadium nitrate? Doesn't that tell you both components? Vanadium can have a lot of different charges, right? This is vanadium-1 nitrate. This is vanadium-2 nitrate, et cetera, et cetera, et cetera. There's a lot of different versions of vanadium nitrate, depending upon the charge of the vanadium. So what we're trying to find out here is what's the charge on vanadium, so that we can use that charge to build the appropriate formula. And then ultimately we'll write the balanced chemical equation. We're told that 2 grams of potassium are added to the solution, so 2 grams of potassium go in, 0.521 grams of vanadium come out. That's the change that's going on. And we want to use that to determine the charge on vanadium. Now when you get to a more complex problem like this, you want to approach it like this. When we defined equivalent weight, we defined it as molar mass over charge, and that was information that we got from the periodic table, correct? But experimentally, it has units of grams per equivalent. So this is experimental information, and that's periodic table information. But if you treat this as a 4-variable equation, that's how you're going to be working these. It's not going to be the parentheses like what we did before. It's a little bit deeper of a problem. And so we need to treat that definition of equivalent weight in experimental terms and periodic table terms. So if we're looking for the charge on vanadium, then we need to set up that formula, plugging in all the information we have about vanadium. Do we know the experimental grams of vanadium? Experimental grams is 0.521, right? Do we know the molar mass of vanadium? Well, yeah, it's right there on the periodic table. So 50.9415. Do we know the charge of vanadium? No, that's what we're solving for, correct? And do we know the equivalence of vanadium? And the correct answer there is not yet. We can get that from the potassium. So that's the key now. This part is going to look like the previous problems. 2 grams of potassium, 39.0, is that 98 or 89? 98. Thank you. 39.0983 grams is 1 equivalent, because potassium is always a +1, correct? And we know that 1 equivalent of potassium gives us 1 equivalent of vanadium. So we convert our potassium out of grams and into equivalents. And that's not just the equivalence of potassium, it's also the equivalence of vanadium. It's also the equivalence of nitrate, but we don't really care about the nitrate. We're just trying to relate vanadium and potassium. I'm getting 0.0512, I guess. 0.0512 equivalents. Question. Now you solve for x. X will be the charge. So it better come out awfully close to an integer. If you solve for x and you get 2.3, then you know you messed up somewhere, because that's not possible. Charge is a whole number, correct? Now if you get 2.97, then that's close enough to 3. What do you get? 5? Comes up very, very close to 5, so we're dealing with vanadium 5. And we're pairing that off with a nitrate. Now, the calculation is over once you calculate out that x is 5. That's the end of the calculation part of the problem. The rest of it is writing the balanced chemical equation. These are the two ions that make up your vanadium nitrate. So the compound itself would be this. And that's formed by potassium reacting with vanadium nitrate to produce elemental vanadium and apparently potassium nitrate. This is a single displacement reaction. Potassium is a +1, nitrate is a -1, so KNO3 is the product. Balancing, we would need 5 nitrates, so a 5 here, which gives you 5 potassiums, and so a 5 here. So there's still a little work to do piecing together that reaction, but the equivalent weight stuff is over once you get 5 as the value for x. Is there a question on that part? All right. Number 35. We've got a metal. We don't know what it is. We don't know who it is, and we don't know its charge. But we're told it reacts with chlorine to form a compound. We know the mass of the metal and the mass of the compound. It wants us to identify the metal and its charge and then come up with a balanced chemical equation. So we really don't have much information this time. We don't even know who the other element is, correct? Grams per equivalent. Molar mass, charge. Plugging in only information about this metal. We know the experimental number of grams, that's 0.363, correct? And we don't know who it is, so we don't know the molar mass. We also don't know the charge, and we don't know the equivalence, and we're kind of stuck. Sorry. But not really stuck, because we can get this equivalence, correct? Based on the chlorine. If there's 1.072 grams of compound, then that's 1.072 grams that is metal and chlorine combined mass. They're both together in this mass, correct? That's the mass of the compound. And apparently 0.363 of that 1.072 is metal. So the rest is chlorine. So 0.709 grams chlorine. And we can turn that 0.709 grams chlorine into equivalents. What's the charge on chlorine? 1. So according to the periodic table, 35.4527 grams, well, what's it say up there? It says 3. Okay. I'll just go with what's on the wall. 35.453 grams of chlorine is 1 unit of charge. That will give me the equivalence of chlorine, but that's also giving me the equivalence of the metal. getting 0.19998, but at 3 significant figures, that would be 0.200. That's a little better. We still have 2 unknowns, correct? 0.363 divided by 0.02. This is 18.15 equals molar mass over charge, neither of which we know. Rearranging that equation a little bit, multiplying charge up to the other side, 18.15 times charge equals molar mass. And that doesn't look any better because we still have 2 unknowns, correct? But one of those is not as unknown as the other because we know charge has to be a small whole number, correct? So this is where you start playing possibilities. But is there a question in getting to that point? If charge equals 1, what would the molar mass be? 18.15. Is there a metal on the periodic table that weighs 18.15 or something close to that and is a +1 charge? Nothing even close. The closest thing to 18 is fluorine, and that's solidly in non-metal territory, right? So that ain't it. If charge were a 2, that would be 36.3. Does that look like anybody you know? 36.3 is closest to chlorine. That's still solidly non-metal, right? So that ain't it. If we try 3. 54.45. Thank you. How about that? Try 4. 72.6. How about that?
Have to be exact.
It's not going to be exact because of rounding errors, but it should be very, very close. That's what, 70 what? Germanium is 72.59. It's extremely close. Is +4 a reasonable charge for germanium? If you remember back to electron configurations, that's the column that had 4 valence electrons, right? And so, yeah, it could lose 4 electrons and be a 4+. So what you know about charges makes sense for germanium. That molar mass is dead on for germanium. Ta-da, it's germanium, right? And you could go on with 5 and 6 and 7 if you wanted to, but you're not going to find anything closer than that. That makes sense, okay? Question about that. Do you see how that works? We don't have enough information in the problem, but based on what you know about charge properties of the periodic table, metals and nonmetals, we can piece this together, right? We ran a list of possibilities and only one of them made sense. All right, let's go back to that original one. Give this a shot now. Oh, I was supposed to do the balanced chemical equation on that last one too, wasn't I? I forgot that. Okay, just doing that real quick. We're reacting germanium with chlorine, which is diatomic. We figured out that germanium is a +4. We knew already that chloride was a -1. So piecing together these electrically means GeCl4 has to be the product. And then balancing the equation would require 2 here.
Work on 8. When is your next exam? Yes, the Monday after Thanksgiving. So this is the last class of material. No. Yes? Yes? No. This is next Monday. Monday before. Next class, right? We've had 2 days on gas law. We've had this 1 day on equivalent weight. You're looking at an extremely math-intensive exam. Not much concept at all here. Culminating in this, I guess. When you get this one done, let me come around and check your answer. When you get it correct, you are free to go.
You say diatomics matter with this?
Doesn't matter.
It doesn't. How close is